This is the first video of 6 cases of different values of B and Q and A. In all the cases, I've included the standard equation of an exponential equation, type 1, where A is greater than 1, and type 2, where A is a fraction, and we rewrote it as A to the minus x, where A is greater than 1. In this example, B is greater or equal to 1, Q is 0, so that Q is 0, and A is greater than 1. So our first graph is 2 to the x, which in this case I consider my mother graph. And my domain is all the real numbers. My range is everything above the x-axis, which is from 0 to infinity. 0 is not included. I do not have any x-intercept because 2 to the x can never be 0. And we do not have vertical asymptote, but if we look at the y-intercept, that happens when y is equal to 2 to the x, but x is equal to 0. So therefore, y is equal to 2 to the 0, which is equal to 1. That is my y-intercept, and I will zoom into the graph just now and show you. On the red graph here is represented by 2 times 2 to the x. So the domain here is still all the real numbers. The range is still from 0 to infinity, 0 not included. In this case, my y-intercept is 2 times 2 to the 0, which is 2 times 1, which is equal to 2. My horizontal asymptote is still the line y equal to 0, or the x-axis. Let us look at the graph of G. The green graph here is y equal to 2 to the x. The next one is y equal to 2 times 2 to the x. We can also write that 2 times 2 to the x as 2 to the 1 times 2 to the x, so that will be 2 to the x plus 1, which is equal to 2 to the x minus 1, in which case it will be the green graph shifted 1 unit to the left. Green graph shifted 1 unit left. And we can see it here, from there to there is 1 unit, from there to there is 1 unit, and as we had it before, we also notice that if we look at y equal to 2 times 2 to the x, where my b is now 2, then it means I take the value here, which is 1, and I've stretched it 2 units to get to the next value. So this is 1, this is 2. If I look at another point, like for instance here at a equal to minus 1, then I take a half, because here we have a half, and that is stretched 2 in the vertical direction, and that will give me the point 1. So here we have 2 ways to get to the graph of G, which is the red graph, and note that the y-intercept, we calculated that to be 2, because 2 times 2 to the 0 is equal to 2. So that is my y-intercept there at 2. What I want you to notice is that when we look at the graph there, which is on a smaller scale, then it looks as if all these graphs cut or at least touch the x-axis. But if you zoom in, this is the value x equal to 6. Then you see they're going rapidly to the line y equal to 0, which is this line here, but it never touched the x-axis or the line y equal to 0. We had the green graph and the red graph. So now the blue graph, our b value here is equal to 3. First of all, the domain is still all the real numbers, and the range stays exactly the same from 0 to infinite, 0 not included. I do not have an x-intercept, so there's no x-intercept. We don't write that equal sign there. And the y-intercept, that happens when y is equal to 3 times 2 to the 0, which is equal to 3 times 1, which is equal to 3. I do not have any vertical asymptote, but my horizontal asymptote is again y equal to 0, which is the x-axis. When we look at the orange graph, p of x equal to 4 times 2 to the x, we see that our b value is now 4. We have a domain of R, and our range is again from 0 to infinity, 0 not included. We do not have an x-intercept because we cannot have 4 times 2 to the x equal to 0. And my y-intercept will be 4 times 2 to the 0, which is equal to 4. I do not have a vertical asymptote, but my horizontal asymptote is again y equal to 0. And that happens at the x-axis. If I label my graphs again as y equal to 2 to the x, y equal to 2 times 2 to the x, y equal to 3 times 2 to the x, and y equal to 4 times 2 to the x, then I see that for the orange graph, I have a value of 8 for x equal to 1. I have a value of 8 for the orange graph, but for the blue graph, I have a value of 6, and for the red graph, I have a value of 4, and for the green graph, I have a value of 2. And I know that 8 is greater than 6, is greater than 4, is greater than 2, which means that the orange graph lies above the blue graph, it lies above the red graph and above the green graph when x is greater than 0. It also happens at the intercepts. The orange is still above the blue, above the red, and above the green. We see that on the left hand side we have again, this is a value of half, then it stretched 2 times to get the value of 1, and it stretched 3 times to get the value of 1.5, then it stretched 4 times to get the value of 2. But again, the orange graph, we have 2 is greater than 1.5, is greater than 1, is greater than 0.5. So on the left hand side, for x equal to minus 1, we also have the y value of the orange graph is larger than the y value of the blue graph, and the y value of the red graph, and the y value of the green graph. We notice that the y-intercepts will be 1, corresponding to the b value 1 here, corresponding to the b value here, and my b value here is 2, and that is the same as my y-intercept here. My b value is 3 for the blue graph, and my b value is 3. That corresponds to the y-intercept here. And for the orange graph, my b value is equal to 4, and that corresponds to my y-intercept here. So my green graph, I can say that 2 to the x is less than 2 times 2 to the x is less than 3 times 2 to the x is less than 4 times 2 to the x, which we can easily see when x is equal to 0. Just as for the red graph, the blue graph is now this value, 1 unit in the y direction, stretch vertically 3 units. So this is 3 and this is 1. And for the orange graph, I have 1 unit here, and then it stretch vertically 4 units in the y direction. So that is on the the green graph, which is equal to 1, is less than the y-intercept of the red graph, which is 2, which is less than the y-intercept of the blue graph, which is less than the y-intercept of the orange graph. This is where x is equal to 0. So we can look at all these functions as vertical stretches, and the larger the b value is, the more the graph will be above the mother graph here, which is y equal to 2 to the x. What we also can say about the orange graph, this is y equal to 4 times 2 to the x, which is equal to 2 squared times 2 to the x, which is equal to 2 to the x plus 2. That is equal to 2 to the x minus 2. In which case 2 to the x, y equal to 2 to the x, is shifted 2 units to the left. Let us check that on the graph. If I look what happens at b equal to 1, then I see I have the same y value, and we have stretched 2 units to the left. If I look at the value at 0, then I have to move 2 units to get to this corners here, which is minus 2, 1. Let me just write it in black. Minus 2. And if I look at another point, say from A, where x is equal to minus 1, then 2 units will land me at this point here on the orange graph. So we can either do it as a horizontal shift, or we can do it as a vertical stretch. In this case, I've said that the green graph, the intercept of the green graph, which is 1, is less than the intercept of the red graph, is less than the intercept of the blue graph, is less than the intercept of the orange graph. And also for x greater than 0, I've just labeled the points here and see that the green graph is below all the other graphs, and here the green graph is below all the other graphs.